Well, thanks very much. And I regret a great deal in not being there in person, as I have several times, many times in the past, the last 20, 25 years, to various meetings. So I hope again in the future that will be, I'll be there. But anyway, I'll do my best to make this plausibly interesting talk for you, even from this distance. Okay, so stop me if there is some problem with hearing me or anything like that. So this talk is about, as the title says, it will be a little bit about the spectrum of flux tubes, something about glueballs, and something about topology in SU engaged theories. Although glueballs are not really part of the this meeting, I thought I would just start with that briefly, because that will lead me on to discuss topology a bit, partly because the freezing of topology in the Monte Carlo process becomes relevant to calculating glueball spectra. And that will lead me to saying something a bit more about topology. And then I'll go on to say a little bit about flux tube spectra, but I won't have much time for that, I'm sure. So there'll be a rather a short presentation, and you'll hear quite a bit more from the next speaker, Michele Casele, about this subject, I'm sure. So the relevant papers, if you want to look things up in more detail, there are a couple of recent papers on the glueball spectrum topology and so on, which are with, and all this work was done with Andreas Athanadoru. The flux tube spectra are also with Andreas. We're just writing the very long paper, but there are a couple of talks that he's given, which are now in the archive. And then there is a little note on some extra methods for calculating the topological charge, which I'll mention during the course of this talk. Well, let me start with something very, very elementary, which you all are familiar with, calculating energies from Euclidean correlators. So we take the correlator of some operator, phi, at some time, and over some time interval, the normalized correlator, you can expand that in a set of energy eigenstates in the usual way. And if you're on the lattice, your time is a certain number of lattice spacings. And then as you go to large times, the slowest falling exponential, which is the ground state, will dominate. And you will have a dependence like this, from which you can read off the energy in lattice units, because NT is what you know, the number of lattice spacings, and you read off the energy in lattice units from your calculation. And indeed, if you have a very accurate correlator, you can also calculate some excited states. However, that is notoriously difficult, and it's much more efficient to do something I won't go into, but many of you will be familiar with that, which is a kind of variational calculation where you have many operators and you're basically looking at all possible linear combinations of these operators and doing a variational calculation to pick out the ground state and then systematically remove that and then pick out the first excited and so on. So that's a efficient way of reasonably efficient way of calculating excited states, which pretty much everyone uses. So this, if we want to calculate glueballs like this, then our operator is typically the trace of a contractible loop or path-ordered exponential of the gauge potential around some closed loop, a contractible loop on our space-time volume, a spatial volume. It will have, we give it by taking rotations of it and taking parity inverses and charge conjugation and so on. You can give it quantum numbers. You can form linear combinations that have quantum numbers which have certain rotational properties. Spin belong to irreducible representations of the rotation group, have parity in charge conjugation. And if you're interested, as I am here, in masses, primarily, you want to have the energies to have zero momentum. So you choose operators that have zero momentum. You make them translation invariant. Just sum them up over the whole time slice. So that's glueballs. And then flux tubes. Well, flux tubes, the way I will be calculating flux tubes is by taking the flux tube to be winding around a spatial torus. So that's a typical operator for that. The basic operator for that would be just the sort of polyacute loop that goes around through the periodic spatial boundary. And if the period of the spatial lattice is L, that flux loop is length L. And then, of course, you have more sophisticated versions of all these operators rather than these elementary operators. But that's a basic operator, if you like. That flux loop will also have some quantum numbers because you can have rotations around the flux loop. So there's a rotational quantum. There's a spin, although that's a kind of two-dimensional spin because it's around the axis of the flux loop. I will concentrate. You can have non-zero momentum, of course, along the flux loop. And we've calculated those energies as well, but I won't discuss those. We will just have zero momentum in this particular, whatever I show you. And there'll be parities as well. So there'll be quantum numbers attached to the flux tubes. So that's how you calculate the energies. And once you've got a couple of energies, you can do a continuum extrapolation. I mean, this is a calculation of one lattice spacing, but and you don't really want your results in units of the lattice spacing. So take ratios of two masses you've calculated, and then the scale drops out. Of course, there's still a residual A dependence, which is the discretization effects. But as the lattice spacing becomes small, if it's small enough, then you know that with the plaquette action that we're using, going back to the work of Szymanczyk a long time ago, the leading corrections are order A squared. So you can do an extrapolation of this kind, an A squared correction with the intercept being the continuum mass ratio. And in practice, what I will do is I will use this as a scale. Different people use different scales, but since we calculate the string tension quite accurately at the same time, we will give our masses in units of the string tension. So mu will always be the square root of the string tension, and the masses will be in units of the square root of the string tension. And in SU3, you can hazard a guess as to what that means in MEV, as I will show you later. So now you have, after doing a number of calculations at different lattice spacings using this method, you, with your Monte Carlo evaluation of these correlation functions, you have continuum mass ratios. And then you can ask what happens as a function of n, and can you do an extrapolation to n equals infinity in SUN. And again, the leading correction should be 1 over n squared. So you can do, once n is large enough, you do just an extrapolation of this kind on your masses, and that gives you the n equals infinity masses. So, so that's a quick summary of this for various steps. And let me give you, at the same time, let me give you examples. So here is an SU8 calculation, and here are correlation functions for that particular lattice at a lattice spacing that corresponds in units of the string tension to 0.13. So if you remember, the string tension in SU3 is approximately the inverse of half a Fermi. And so this is roughly like 0.07 Fermi if I was using such, just to give an intuition. Of course, there aren't any Fermis, real Fermis here. We're not in QCD. Still, so it's quite a small lattice spacing on a reasonably large lattice. And here are some correlation functions. The first one is for the flux tube. As you can see, that happens to be the lightest object. It has no overlap onto glue balls. A pair of flux tubes can have an overlap onto glue balls. A flux tube and a conjugate flux tube can, but the flux tube itself does not, because of the symmetry reason. And the center symmetry argument, the usual center symmetry argument. Then there is the lightest scalar glue ball here, which is this line. And then the lightest spin 2, which is the open points, and so on. There's a few examples here, including the first excited scalar glue ball, which these solid points again, these bullet points again down here. And then there's the lightest negative charge conjugation particle, which happens to be a spin 1, which is down here. So these are just examples. This is not the most reliable way of presenting. So what I was showing you is that you can get nice exponentials which go, which have a good overlap, so that they go near 1 here. but it's not really the best way of, it's not the most convincing way of presenting this argument, because it's notorious with these kind of logarithmic plots that since you can't see the errors, you don't really know whether this is a good fit or not, although it looks like it on this plot, but the errors are much smaller than the size of these points, so you can't tell. So I really should show you effective mass plots, and in our papers, that's what we show. We don't focus on these kind of nice plots, but the effective mass plots. So, so these are the some examples of correlation functions, and here we have some continuum extrapolations. So that was for one, that was for SU8 with one particular lattice spacing. Here is SU4 with 6 different lattice spacings. Here is the value of the lattice spacing as a unit of the string tension, where the string tension was, of course, calculated in each one of these calculations. Therefore, I know what this value is. And I have the ratio of the glue ball to the square root of the string tension. And I show you what happens for the lightest and first excited glue balls, the solid circles. And then these other points are the lightest and the first excited tensor, T2++. Now you can see, you may be asking, why am I using continuum? You may be asking about this continuum spin that I'm using. Well, of course, in the continuum limit, these states have the continuum spin, but on a lattice, on a cubic lattice, the irreducible representations of the rotation group are actually, it's a much smaller rotation group, just 90-degree rotations. And there are 5 irreducible representations, in addition, another 5 for parity, but for say positive parity, 5 irreducible representations for the rotation group. 2 of them are 1-dimensional, 1 is 2-dimensional, and 2 are 3-dimensional. And then in the continuum, of course, you've got an innumerable number of representations, each one of dimension 2j plus 1, j is the spin. For example, the tensor is 5-dimensional in the continuum. So once they're here, they belong to some 5-dimensional representation. And what you can see is that 2 of them are in the 2-dimensional E++ representation and 3 in the T2++. And the fact that they belong to the same continuum spin is provided, the evidence for that is provided by the fact that these 2 sets of masses from the 2 different lattice representations are essentially degenerate. So for low-lying masses, you can actually infer the continuum spin in this way. But you can't do it for more massive states, because then you start getting a lot of different states close to each other, errors get larger, and this degeneracy begins to be very ambiguous. But here at this level, for states of this mass, it's unambiguous. So there are the states, I can show you a number of states with their continuum spins, and then a lot more states which are just in the representations of the lattice rotation group. And one day we will try to do better than that and have spins for those as well. And that will be important if we want to, for instance, test the kind of idea like, do glue balls define a Pomeroy trajectory? So you need quite a few higher spins for that. Okay, n equals infinity extrapolations. Well, here's a mass. So these are now continuum ratios, and I've picked the ones for spin 0, and you can have they extrapolate them to n equals infinity. This is SU2, SU3, and we went up to SU12 in this calculation. Probably the SU10 and SU12 calculations are not as precise or good as the lower ones. Obviously, things that get more expensive as you go to larger n, and that's the main reason. But they're pretty good, I think good enough to be used here in these plots. So as you can see, we can get pretty excited. We have precise values for the continuum mass ratios and precise values for the, although I'm not showing you the numbers, you can find tables of numbers in the papers. You have precise values for the extrapolated values at n equals infinity. And this is the kind of stuff that is, these are kind of the spectra which are useful for people doing, trying to calculate, well, as you know, Kobe and other people, you've heard talk by Kobe, but there are other people, holographic calculations where they want to calculate spectra and want to check their calculations, which are ultimately, they would like to say something about QCD, and they would, or pure gauge theories, and they can check them against these lattice calculations. This is, if you like, the data there, which experiment can't really provide, but our computers helpfully can. And here is a same thing, not for spin 0, but for spin 2, large N extrapolations. And okay, so in doing these calculations, of course, one is assuming that one's Monte Carlo is ergodic, that you really are sampling the space of field configurations. Of course, there is critical slowing down. So as you make the lattice spacing smaller, the things are more highly correlated between sweeps, heat bath sweeps, or whatever Monte Carlo you're using. And so you have to do more calculations to get the errors down. However, there is also, in addition, there are some quantities which break, where ergodicity breaks down much more rapidly than for the usual quantities. And one of those is topology. So by the time you get to our SU8 calculations, topology is no longer changing when we do a Monte Carlo. If you do 2 million sweeps at a reasonably small lattice spacing in SU8, there is no change in the topological charge from the initial topological charge. So we're not really sampling sectors of different topology. In a sense, that's of course a good thing, because in the continuum theory, which we're trying to approach, we know that fields of different topological charge cannot be smoothly deformed into each other. And our Monte Carlo is an approximation to a smooth deformation. So we're approaching the continuum limit, and it's getting harder to change topology. But why is it getting so much harder? Well, one reason, good reason, is the following, and it's been known for a long time as this topological freezing. It's really the following. So we can now change our discussion to topology. So the basic idea is that if you have a field with topological charge Q, say, some integer Q, which is on a periodic finite volume, how does it change? Well, of course, instantons and anti-instantons can annihilate, and they're constantly doing that, and there's nothing special about that. Pairs of instantons and anti-instantons can be formed and annihilate. So that is happening all the time in the volume. However, to actually change the topological charge, that involves an instanton shrinking gradually. I call it an instanton. Of course, when it's big and one Fermi across, who knows what you should call it. But anyway, let me call it an instanton. The topological charge shrinks. And eventually it shrinks down to a lattice spacing. At this point, the topological charge is indeed, once it's very small, you can describe it semi-classically. So we can talk of an instanton. And you can talk of the core of the instanton, maybe slightly deformed by fluctuations, but there it is, the core, and the core shrinks within a hypercube. Once it shrinks within a hypercube, all the links on that hypercube become pure gauge, and you no longer have an instanton. Instead, you have a gauge singularity in the gauge potential, but this is a singularity that the field strength doesn't see. So it's irrelevant, if you like, from that point of view. And indeed, that's how originally you have a non-zero topological charge on a compact periodic volume, because any net topological charge is matched by gauge singularities somewhere in that volume. If you were in the continuum, that's how it would be. So that's how you get rid of it, how a topological charge changes. It disappears within a hypercube, but in the process of shrinking down, it becomes very small. So an upper bound on the probability of this whole process is the probability of finding a very small instanton with a size of order A. And there I can use, once A is small enough, when the lattice spacing is small enough, I can use semi-classical formulae. And basically, if you go through the density of instantons, which are on a size scale of a few times lattice spacing, is A times the lambda parameter with this power, where I've used a one loop formula for the running coupling. I've gone from 8 pi squared over g squared, e to the minus 8 pi squared over g squared, down to using the one loop formula, which indeed, if the lattice spacing was small enough, would be reliable. Frankly, we're not in the regime where it's likely to be reliable in any of our lattice spacings, but just in principle, this is what happens. And what you see here is that as the lattice, if you're at a fixed lattice spacing and you increase n, then since a lambda is less than 1, much less than 1 typically, the density will fall exponentially now. So the probability of getting a change in topological charge has this extra exponential factor, suppression. And if you instead keep n fixed but make a smaller, it's a power-like suppression, extra, but quite a large power when n becomes, as soon as n is not, even when n is equal to 3. For n equals 2, it's a very small power. That's a very weak suppression. And things get a bit messy in SU2 for that reason, in the topology sense, when you look at the vacuum. But this is, so this is quite easy to understand, this factor. There may, of course, be other factors. Indeed, there is a factor from what happens once it starts shrinking within a hypercube. You know, that depends on the lattice action. We're using the plaquette action, but that would depend on the lattice action. So there's certainly other factors, but this gives you an upper bound. And this upper bound is already very strong. It tells you that things disappear very rapidly. The density of instantons disappears very rapidly as small instantons, and therefore the probability of changing topological charge cannot be more frequent than this. So let's have briefly show what one actually finds. If one, so one can define tau of Q as being the average number of Monte Carlo sweeps in between a change of topology. And the argument here is that it should go as A goes to 0 at fixed n, or as n goes to infinity at fixed A, it will go to 0 very rapidly. So how does it go to 0? Well, here we are looking at, there were 3 points. There were 3 values of n, 8, 10, and 12, where we had lattices of comparable lattice spacing, where we could still, it was a coarse lattice spacing. You can see this is a coarse lattice spacing, so we could still get topology change. And if you look at the average number of sweeps between a change of topology against n, you see that it does fall on what is an exponential, because there's a log here against a linear n. And then we have a finer lattice spacing, about half of that, which takes us from SU3 up to SU6. Here the error is quite large now, because on this logarithm, this is logarithm, remember. But anyway, again, this looks like an exponential. So that fits in with this exponential behavior, although the numbers, I'm not sure if they, you know, if the slope is, I didn't try to compare the slopes with any theoretical prediction here. Then if you look at what happens at fixed n, but varying lattice spacing, then that looks, I plot a log against a log, and that is consistent with the power. So roughly speaking, what we're seeing is what we would expect, roughly speaking. So there's no big mystery about topological freezing, and that's been known right from a very long time ago. But you can see with this kind of data, you can see quite accurate, sort of quite accurate evidence for things being exactly as you expect, pretty much as you expect. Now, the question then is, does this freezing matter in our calculations? That's the immediate question. And my belief is that it doesn't, for the following reasons. First of all, if we're looking at large n, we know that the fluctuations of a correlation function, like a glueball correlation function, and the fluctuations of Q squared decouple with corrections of order 1 over n squared. And this is to do with the fact that we're sitting in a vacuum, and to look at the correlation function like that, you would take the theory, put in a theta vacuum, e to the I theta times q, and you would take derivatives with respect to theta to bring down factors of q, which you wanted in your correlation function. And so what it all depends on derivatives of that partition function of the path integral with a theta term when you take derivatives with respect to theta. Now, why is that actually almost flat at large n? The reason is, this goes back to Witten's discussion in '98 about interlaced theta vacua. So yeah.
Nanti lampunya mati, susah belinya loh itu.
Is that a question? No. Okay. Anyway, so Witten's interlaced theta vacuum is, you know, the fact that, as you're well aware, you've got an action with 1 over g squared times integral f squared, but really the large n counting tells you that if you want constant physics, you have to keep g squared n fixed. So it's 1 over g squared n. G squared n is the relevant thing. So if you have another term, which is theta times integral of ff dual, the thing that you keep fixed is theta over n. And that means that the periodicity is 2 pi n, not 2 pi. So the vacuum we're sitting in has a periodicity of 2 pi n, and as n becomes large, it becomes very flat at theta equals 0. So you get these, the derivatives go to 0 with respect to theta. But of course, you can't just have that because if you look at e to the I theta q, it manifestly is periodic in 2 pi. So what you need is a lot of different vacua that are shifted by 2 pi, these interlaced theta vacua. So you maintain both periodicity in 2 pi and have a individual vacua that have periodicity of 2 pi n. And there were some nice lattice calculations going back quite a long time ago in the early 2000s by Luigi Del Debbio. I think it also involved Vicari, Panagopoulos, I think, might have been someone else, who actually did lattice calculations, and they showed that they got evidence for this kind of behavior about 15 years ago. So it's both got explicit and also the theoretical background, right? So that's so at large n we're not too concerned. We don't have in practice any freezing for n less than 5 in our calculations, and almost none in n equals 6, a bit of the smallest lattice spacings. And then it freezes once you get above SU8, once you're in SU8 or above. But there we did, in order to see whether we were in the regime where the things didn't depend too much on Q, we did an explicit check, high statistics check, where you had mass calculations where everything was Q equals 0, and mass calculations where a whole distribution of Q, which we put in by hand. And in fact, within errors, there was no difference. So there's no difference. So I think n equals 8 is already large enough within our kind of statistical errors. And we improved that by giving you would start off with, say, 40 different sequences, Monte Carlo sequences, and you would have starting configurations which had a different distribution of topological charges. So on the whole, I think that is no problem for us. However, you might want to do better, because one of the things you cannot do is calculate an SU8. You can't calculate the topological susceptibility because there isn't any variation. You're putting it in by hand. So there's various things that depend on Q intrinsically that you can't do unless you overcome topological freezing. So one of the various ways of approaching here, one is to take a very large physical volume and then do calculations in a smaller physical volume, 10 Fermis on the side and then do a volume 2 Fermis. Another thing is to use open boundary conditions at one end so that instant ones come in and coming out. I think there's only been partial success with that. I haven't looked at all the papers there. And another recent thing, which is quite interesting, is developing an idea of Hasenbusch from a couple of years ago, which you put in a defect and you update in such a way that you maintain the correct distribution that you want, but you can bring in instantons through the defect in and out. And there is, for example, a nice paper recently, very recently, by Bonanno et al. Doing precisely that. And there's a couple of earlier papers. Okay, so that's how you can go around, as far as I know, about freezing. I don't think it's important for the glue ball calculations, but it is relevant for various other things. And it may be, if you want to do glue ball calculations sufficiently accurately, much more accurately than we have done, it may become relevant there too. Probably will. Now, let me say a few things about calculating topological charge. There's the usual formula in the continuum, which you can then translate in a naive way onto the lattice. You have to sort of anti-symmetrize that, but for smooth fields, gives you the usual topological charge. On rough fields, the ones you have in your Monte Carlo, because this Q doesn't really have a topological interpretation, the lattice operator is not a topological, unlike this. There are renormalization factors, there's a fluctuation factor, and there is a renormalization of the topological charge itself. And it turns out, unfortunately, that this Z of beta, wherever one does calculations, this you engage theories, is much less than 1. So if you have a field with a unit topology, the actual integral of this quantity is very much less than 1, even if you average over many fields, enough fields to see the average. which means it's hard to see in the midst of all these fluctuations. You know, sometimes you're lucky in these lattice calculations, sometimes you're unlucky, and I think this is one case where we've been a bit unlucky. Anyway, so what you want to do, one way to proceed is to remove these, if you want the total topological charge, remove the perturbative fluctuations, these high frequency fluctuations, by smoothing the fields locally so that Q does not change. One way of doing that is to replace the heat bath by an action minimization. Take each link, instead of doing a heat bath step, choose a new link matrix such that it minimizes the action, local action, the plaquettes around it. That's easy to do. That's a cooling sweep. Do a few cooling sweeps, and then you see the topological charge appear in a nice way.
Sorry,
there are other algorithms.
Mike, sorry, you have 10 minutes, including discussion now.
Okay. So there are other ways of doing this, which I won't comment upon, but you can see them on my slide. If you do cool, here's an example of SU8. You have after 20, so you have a large, I don't know how many, I had 25,000 fields that I cooled here. After 20 cooling sweeps, the topological charge, the lattice topological charge, is the solid point. So you can see it's right on top of integers, very close to the integer values, and very sharply peaked. And even after 2 cooling sweeps, if you just done two sweeps from the original hot lattice, you get this, which already shows a nice sharp peaking structure. Okay, I will go through that since I don't have so much time. You can calculate the topological susceptibility. And let me just say, and if you do that, this is against n, you find up to SU6. So I managed to get up to SU6. As I say, we can't do higher than that because of topological freezing, but that already allows you a nice extrapolation to n equals infinity. Get an extrapolation like this. And in particular, if you look at the SU3 value, which we calculate quite accurately, it's units of the string tension, you get something like this. And then if you convert the string tension to the somma R0 parameter using a fit between the two, which we do, we get an accurate value for that. And then the R0, Sommer has his favorite value, which was from looking at QCD calculations on the lattice with light fermions. And he gives a value in Fermi units. And if you use that, then you get 206 MeV for the susceptibility. Okay, let me, so we have many consistent methods for the total topological charge. And then which is nice, some are more expensive than others, but they're all, as far as we can tell, consistent with each other, whether you use Dirac zero modes, whether you use Wilson flow, whether you use cooling. And you can see where they differ. It's to do basically with lattice artifacts, which you can isolate and you can identify. Now, calculating the topological charge density is more tricky since it's altered by any kind of smoothing procedure. The actual density changes even if the total topological charge remains constant. And if you want to do that, well, I decided to just look at a couple of old ideas. I'll only mention one here, which came up in a paper before we had the archive, so I can't give you the archive reference. But recently I put in a note on the lattice archive, which works a bit more on those particular methods. So one of them is very, very naive, simple, which is you've got a field, lattice field, which is very rough. It's been generated by Monte Carlo. You want to know what is its topological charge and topological charge density. So you want to average out the local the high frequency fluctuations without doing any smoothing. Well, one way to do that is to just take a couple of Monte Carlo steps, heat bath steps at the same value of beta as you generated the original field. That gives you a new field, which is almost the same as the old field, but the high frequency things would have changed a bit. And then you repeat that with different random numbers and you create an ensemble of fields, which are just say 3 sweeps, Monte Carlo sweeps away from the original field, and you average the topological charge density on these fields. And if you do that, then, well, first of all, you find the average topological charge is nicely, so here is the average topological charge against the true topological charge of 5 different fields. You start with 5 different fields, one with -1, another one with topological charge 0, 1, 2, 3, where these have been established by 20 cooling sweeps. So you have 5 fields, and on each one you do 10,000 of these, generate 10,000 fields, which are just 3 Monte Carlo sweeps away. And you calculate on those the average topological charge, and they indeed follow a nice straight line here with normalization factor, which is exactly what you find when you calculate normalization factors in the conventional way. So, and they differ from each other. They, you know, if you have a field that has this value, it's definitely not got this value. So the errors are much smaller. So you can certainly identify topological charge very, very well this way. No smoothing. If you look at the topological charge density, the average topological charge density, you get a nice something or other, you know. You do get a density. This is a profile looking at summing up of the topological charge in each time slice, and you get a nice profile like this. And you can compare it, for example, to what you get after 2 cooling sweeps of the original field, which had a topological charge of -1, and they follow each other pretty closely. Now, with cooling, that curve, the cooled curve, would change with the number of cooling sweeps. I picked 2 because it was close to this, and this suggests that if you do 2 cooling sweeps, you're very close. You're already pretty close to getting what was in the underlying field. Otherwise, I wouldn't have known that. Okay. So let's move on to, in the last 5 minutes or so, let me quickly move on to the spectrum of confining flux tubes. I'm not going to say too much about this because of the limitation of time. It's a very big subject. So the idea here is to calculate the energy spectrum of the flux tube winding around a spatial torus of length L for various lengths L. It has a certain number of relevant quantum numbers, including spin, 2 parities, 1 transverse parity, 1 along the flux tube. The quantized fluctuations, the fluctuations of the flux tube, when you quantize them, give you sort of massless phonons on this string. And the interesting question is, what is the effective action? And is there anything other than phonons there? These massless phonons. The massless phonons are basically Nambu-Goldstone bosons, which are related to the spontaneous breaking of translation symmetry, of the bulk translation symmetry, by having a particular string in a particular position. So we know now, what do we know? Well, we don't know too much, but we do know that if you are in 26 dimensions, bosonic strings have a spectrum. This was long time, Goddard et al. Did this, Raby, Thorne. You have a spectrum like this. I will just look at, this is for non-zero momentum and any number of phonons, left and right moving phonons along the string. So this is a spectrum that is there in the literature. And the interesting thing is that it works very well. So here is the observed spectrum. And the solid lines are this Nambu-Goto GGRT spectrum predictions taken from 26 to 4 dimensions. And here are the observed lightest particles with various quantum numbers. So the very lightest 0++ is the ground state, and that's where you get the string tension from that. Once I've got the string tension, I can rescale my coordinates so that I have nice coordinates where I can compare calculations from different groups and different lattice spacings, and they should fall on top of each other in these units. So here's the energy in units of the string tension, the length of the string in units of the string tension. And so you get this 3 of the states of the 4 states that should lie here on this thing, do indeed lie in it pretty closely, approach it quite closely, but there's one which is way off, an outlier. So is that significant? Well, before coming to that, first of all, it's very interesting that all of these states do lie very close on these lines. After all, if you look at this value here, by the time we get to around 2, this flux tube is not much longer than it is wide, so it's hardly a string. And yet this string theory prediction seems to work very well. And works very well out here as well. So, and in particular, it's worth noting that the deconfinement, when the volume becomes small enough, you go through a kind of a analog of the deconfining transition, a finite volume transition, which occurs around 1.5. So we're quite close to the minimum volume where we can actually do anything at all, the minimum length where we can do anything at all. After that, you lose the confining flux tube. So, so you have this spectrum, and the questions immediately are, why is it so good? First at large L, why is it really following? And I could have shown you things here as well. I don't have them with me here, but we have results for these states as well. Well, the fact is, there is an explanation for this nowadays. And if you take this square root formula and you expand it in powers of 1 over L, what you find is that the first few terms are actually universal. You can prove that they're universal. So the first universal term is the famous Lucia correction, 1 over L. But it turns out also the 1 over L cubed and 1 over L to the 5th terms are universal for the ground state and up to 1 over L cubed for excited states, and analogous statements for 2 plus 1 dimensions if you want those. And a recent, this is developed very much over with a number of papers by Ofer Acharoni and collaborators, and a recent paper is the one with Komargodski, which will refer to those. A very interesting question is, why is it so good at small l, where the flux tube is hardly a string, pictorially? Well, there's a interesting theoretical development there by Sergei Dubovsky and collaborators, and a reasonable paper to find out about it is here. And basically it takes, it's because the theory, you can argue, is nearly integrable. The phonons have a scattering leads to phase shift. There's a phase shift between the scattering. And then if you use a beta ansatz for all the scattering with all the phonons that are circulating around on this small volume, like a gas, if we were talking about finite temperature, there will be this gas. You have the same thing, but in a spatial circles, spatial propagating phonons. The interaction with them gives you something very close to what we observe. So we're beginning to understand both why this works so well. Then finally, is this 0 minus minus outlier state, the extra state that didn't really fit on the curve, is that a massive state or not? Well, the answer is almost certainly yes, because if you look at the next excited 0 minus minus, so now I've put all together all our calculations, SU3, SU5, and SU6, and the different couplings, which are different colors and different shapes, but this is essentially the lightest 0 minus minus, and this is the first excited 0 minus minus. Now, so the question is, was this lightest one a stringy state? If this was a stringy state, then the next one, there's no room for it on this thing, because only one 0 minus minus should be on this by universality argument. So this should be going up to there, but it's not. It's going down to here. So this looks very much like the stringy state, phonon state, and this therefore is something else. And it's a constant amount above the flux tube, so it looks like a massive excitation on the flux tube. And if you subtract the ground state flux tube, indeed you get this nice constant piece here, which gives you a mass of 1.85, which is just slightly more than half the lightest blue ball mass, whereas the first excited 0 minus minus is clearly going down to the ground state level of the 0 minus minus here. So this is the sort of thing what one is doing here in this. I won't spend, since I'm running out of time, I won't spend any time on this figure, which doesn't add too much. It's just showing you that you have states in the 0 plus plus sector that consist of 2 0 minus minuses. That's this lot, this thing. It's just twice the original 0 minus minus. It's a 2 0 minus minus state. So this is the kind of thing which one can be doing in this with these flux tubes, is looking for the effective action, looking for what other states there might be on this, the effective action of confining flux tubes. And in a sense, although we now understand the basics pretty well theoretically and numerically, there is clearly there's going to be a lot of interesting things to continue with. Looking, for example, at bound state flux tubes like the K-strings, looking, for example, at flux tubes in where you have adjoint fermions, for example, where you might have fermionic zero modes along the string as well. So there's maybe a lot of interesting things to, and indeed to learn more about the n equals infinity limit, which always promises to be a bit simpler. So yeah, so thank you very much. That's I don't really have conclusions apart from what I just said.